So today we'll discuss the basics of digital logic design, Boolean algebra as well as logic gates. Initially we'll go through the basics of digital logic design and then we'll move on to the Boolean algebra. So in these basics we'll see what is a binary variable and what are the operators that are used throughout this Boolean algebra and how we represent a binary variable. So what is a binary variable? Actually, a variable can hold any value, but when it comes to a binary variable, it can hold only two elements. Either it might be 0 or else it might be 1. If you take an example of a binary system where every quantity is represented only with two elements, either 0 and 1. So that is why the base of the binary system is 2. In the same way here, a binary variable can only accept two values. It might be either 0 or else it might be either 1. And throughout this Boolean algebra, we are going to use three basic logical operators. Those are AND, OR and NOT. So we'll discuss about these operators in the later, and we represent every binary variable with alphabets. So we can represent any binary variable only with the alphabets. They might be the uppercase letters or else they might be the lowercase letters. Now, what is a function? A function is used for representing the relationship between the input and output. So, if it is a binary function where the input contains binary variables and the output expression also involves binary variables. If you can see here, f of variables equals expression, where variables are the binary variables which can hold only two elements, either 0 or 1. And here expression involves operators like plus, dot and complement. For now we call these operators as plus, dot and complement, and we'll discuss what are the terminology that we use throughout this Boolean algebra. And it may also involve variables, it may also involve constants like 0 and 1, and then parentheses. Take an example here where a function f of a comma b equals a complement dot b plus b complement, where the left hand side within the parentheses a comma b, these are the binary variables, these are the binary input variables, and the right hand side within the expression a complement b and b complement are the binary variables, and dot and plus are the operators, right? In the same way, if you take one more example, g of x comma y comma z equals x dot of y plus z complement, where x, y and z on the left hand side are the binary input variables, and on the right hand side it is an expression which involves dot and plus operators along with complement operator, and then the variables as well as the groupings which are nothing but the parentheses. So this is how we represent the relationship between the input variables as well as the output of that particular function. Now these are what the basic logical operators that we use: AND, OR and NOT. And this AND and OR operators are called as binary operators because these operators can operate on two variables. And if we take NOT operator, it is called as unary operator because it operates only on one variable. Let us see, f of a comma b equals a dot b, where dot is the symbol which is used for representing the AND operator. So from now onwards we have to call this dot as AND. So it is f of a comma b equals a and b, and the output of this function is 1 only when a and b values are 1. Okay, if any of the value which is present in a and b is 0, then the output is 0, right? And next is OR, g of a comma b equals a plus b, where plus is the symbol which is used for representing the operator OR. So from now onwards we have to call this as a or b, and the output of this function is 1 when both the operands are 1 or else any of the operand is 1. Okay, and if both the operands are 0, then the output of the function is 0. Okay, and the third function for representing the NOT operator, h of a equals a complement, where this is the symbol which is used for representing the not operator, and it is operated only on a single variable, so that is why it is called as a unary operator. And the output of this function is 1 when the value of a is 0. Okay, and the output of this function is 0 when the value of a is 1. So complement. Right, now let us see the mathematical comparison between these operators. Okay, so 1-bit logic AND resembles binary multiplication. So here 1-bit logic AND reflects the binary multiplication, where 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 1. So it exactly reflects the binary multiplication. And if we take logical OR, where it exactly represents the binary addition except one particular combination, that is this combination. So if you can see here, 1 plus 1 in the binary addition is 2, but whereas in logic AND, which in case of Boolean algebra, 1 plus 1 is nothing but 1. Apart from that, 0 plus 0 is 0, and that is 0 or 1 is 1, and then 1 or 0 is 1, and then 1 or 1 is 1. Okay, so here binary AND, or else the logic AND, represents binary multiplication, and logic OR reflects binary addition except one condition. Right, now these are the truth tables for those operators. So what is a truth table? Truth table represents the relationship between the input variables of a function and its output. Okay, so it is representing the relationship between the input as well as the output, along with the possible combinations of input and their outputs. So if you can see the truth table of the 2-input AND gate, where a and b are the inputs, and the function, output function, that is f is equals, output expression is a dot b, or a and b. Okay, and if we have two input variables, then the possible combinations that we get is 4. So 0 0 0 1 1 0 and 1 1, and the output function is 0 0 0 1. Okay, as we have discussed, if a and b operands are 1, then only the output becomes 1. Okay, and in the same way, if we take a look at the 2-input OR gate, there you can see a and b are the input variables, and the output expression is a or b. So again, the 4 possible combinations, 0 0 0 1 1 0 and 1 1, and the output of this particular OR is 1 only when both the operands are 1, or else when any of the variable is 1. You can see here one variable is 1 here in this combination, so the output is 1, and here also one variable is 1, so therefore the output is 1, and both the variables are 1 here, therefore the output is again 1. But in the case when both the variables are 0, then the output is 0. Now in the same way, as I told you that not or complement is only operated on one variable, therefore there is only one input variable a, and the output expression is a complement or else a naught. Okay, so here if a is 0, then the output expression is 1, and if a is 1, then the output expression is 0. Okay, now here truth table is giving us the relationship between the input as well as the output by using the possible combinations of the input. Right, now let a function f of depends on n variables. How many rows are there in the truth table of function? So the question here is, assuming that one function contains totally n variables, that is from a0 to assume that an. Okay, then how many possible rows here indicates combinations, how many possibilities, how many combinations that you are going to get. So here the answer is 2 power n. Okay, if we take the previous example where you have only two variables within the function. Okay, so the answer, or else the number of rows that we get inside a truth table is 2 power n, where n represents the number of input variables, therefore 2 power 2 is nothing but 4. So 2 power n rows, since there are 2 power n possible binary patterns or combinations for the n variables. Okay, so here n is representing the number of input variables. If there are, for example, if there are 3 input variables, then the possible patterns or combinations that we get is as n equals to 3, so 2 power 3 is 8. Right. So this is how we represent the truth tables. Now logic gates. So logic gates are mainly used for realizing any electronic circuit. Okay, so logic gates are abstractions of electronic circuit, components that operate on one or more input signals to produce an output signal. So these are the gates which operate on one or more input variables or signals, and they'll produce one output signal. Okay, now the operators that we have seen now is AND, OR and NOT, and all these operators are represented with the gates in this fashion, where you can see the symbol of the AND gate, and it is the gate which can accept more than one input and produces only one output, and that output function expression we have seen that is f equals a and b. In the same way, this is the OR gate representation, and it is also a gate which can accept more than one input and produces only one output, and the output expression for this OR gate is a or b. And NOT is the gate which can accept only one input and produces only one output, and here the output expression is h equals a complement. So these are the 3 basic gates which we use for realizing any kind of electronic circuit. In the next session, we'll deal with Boolean algebra and its properties. Thank you.